Okay. Okay. So they say in the diagram below, angle DCB is alpha. The length of AC is h units, and angle ACB is theta. And they showed us everything that we need to do. Or rather, no, that's what I should have said. And this is not a two-dimensional situation. It's just a one-dimensional situation. It's not even 3D. It's just a single dimension, but it's fine. Now here we can see we have three triangles in total. We have the big one, which is a right-angled triangle, ACB, or ABC rather. Then we have another right-angled triangle, which is BCD. And then we have an ordinary triangle, an obtuse triangle, which is ACD. The reason why I'm saying a right angle as well as an ordinary triangle, well, that's because we know that the trigonometric ratios can only be applied in a right-angled triangle. But in an ordinary triangle, you either use the sine rule or the cosine rule or the area rule. That's what I'm saying. Okay, fine. So the angle alpha is in the small right-angled triangle, and the angle theta is in the big right-angled triangle. Is there someone who can tell us what is the size of angle ACB just by looking at it? In other words, the blue angle that I'm showing you here, what is the size of angle AC? What did I say? Did I say ACB? No, I'm lying. I should have said ACD. Yes. Anyone? Come on, guys. What is the size of angle ACD? Okay, maybe it's a little bit challenging. I can guide you though, that's fine. If I told you that the size of alpha is 15 degrees, and I told you that the size of theta is 45 degrees, then what would be the size of angle ACD, the numerical value of it?
It would be 30.
30 degrees. How did you get the 30 degrees, sir?
I said theta minus alpha, so saying 45 minus 15.
So then, what is the size of angle ACD, sir?
Theta minus alpha.
Sir, I'm not sure if you are speaking or what's happening, but I can't hear you.
So I said angle ACD is theta minus alpha.
Theta. Wow. Thank you, sir. You just needed a bit of guidance. Yes, that's just it. All right, you should be able to come up with things such as this one because they do like them. But let's go. The first question says determine the size of ACD in terms of theta and alpha. Wow, I actually didn't see that this question was coming up, but there it is. It's just gonna be theta minus alpha. Then they say prove that AD is h sine theta minus alpha divided by cosine alpha. Well, that's what they say to us. Now, where is this AD? And I said to you yesterday, take these questions lightly in a very simple way instead of proving that AD is that, take it as if they're asking you to find the length of AD. And if you look at your AD, you can see that it is not in a right-angled triangle, which means you can't use the SOHCAHTOA. You can't use the normal trigonometric ratios. You can either use the sine rule or the cosine rule. That's what I'm saying to you. Okay, fine. Now, the easiest thing to do here is really to use the sine rule. Yeah, it's the best way out. But in order to use the sine rule, we'll have to know what is the size of the angle here. But we now know it. It's theta minus alpha. We need to know this angle so that we can find the side opposite that angle. Very well. But that's not enough. We also need to know another pair of an angle as well as a side opposite that angle. Now, since our answer has to have an age in it, then this means we need to use this pair. That's what I'm saying to you in simpler terms. Now then, in order for us to use this blue pair, that's if and only if we know the size of angle D1. And we can find angle D1. How? Yeah, it's a bit tricky as well, but it's not tricky at all. If you just look at it from the triangle that's not right-angled, ACD, it's very difficult to find D1. Very difficult. But we have to begin somewhere, which is in the bigger right-angled triangle, and find the size of angle A. And we're going to use that, or rather find that, by using the sum of interior angles of a triangle. And once we know angle A, then we can go to this non-right-angled triangle and use the sum of interior angles once again in order to find it. Okay, let's quickly go and do that. I know as I'm explaining it, it really seems difficult, but let's quickly show it's not difficult at all. So I'm going to go to the big triangle, which is ABC, and I'm going to find the size of angle A. So I say, if I take angle A, I add it to the right angle, which is angle B. I also add it to angle C, which we know is theta. Then the answer is going to be 180. Well, the sum of interior angles of a triangle. Now, when we take everything to the right-hand side, the 90 degrees becomes negative, and 180 degrees minus 90 degrees will just give us 90, and the theta becomes negative as well. So now we know the size of angle A. So now we can come to angle D1 by saying if we take angle A, we add it to angle D1, and we also add this to angle ACD. Then the answer will be 180 degrees as well for the same reason. But now we know angle A is 90 degrees minus theta. We are looking for angle D1, but angle ACD, we just found it. We got it as theta minus alpha. And everything must be set equal to 180. Now we can see that the two thetas cannot be in the same room, so they do their thing. And now we are left with D1 on the left-hand side. We take 90 degrees to the right-hand side, it becomes negative. 180 minus 90, that's 90. But the alpha becomes positive. So then this is what we have. And now we have the size of angle D1. So now we can use the sine rule. According to the sine rule, the sine of angle D1, which is 90 degrees plus alpha, divided by the side opposite angle D1, which is AC. But we know the length of AC is h units. This will be equal to the sine of angle ACD, which we said it's theta minus alpha, divided by the side opposite angle ACD, which is the side we are looking for. It's AD. But now we can see that we can use our reduction because we have learned the reduction formulae in the first term. 90 degrees plus is in the second quadrant. In the second quadrant, sine is positive. But due to the 90 degrees, we know that sine has to change to cosine. So cosine is going to be positive only because sine is positive in the second quadrant. And this is what we are saying. When you get to grade 12, you will learn that the right-hand side part in the numerator is a compound angle, and you will learn the formula to expand a compound angle. But since you are still young, let's just do things that are relevant to our age. So now we can cross multiply and say, well, AD cosine alpha will now be given by h sine theta minus alpha. And now we divide both sides by cosine alpha. So we can find that AD will be h sine theta minus alpha divided by cosine alpha. Well, this is what we can say. Okay, now then we go to the next question, and this is what it says. They say to us here, please determine the length of AD if it is given to us that h is 17 units, theta is 58 degrees, and alpha is 23 degrees. Okay, let's do that. So this means our duty here is just to do the substitution, and we should be fine. So we now know that h is 17 units. And then we can say, well, theta is now given to us as 58 degrees. Yeah, no, I should have just went to the next slide. Yes, would have made a lot of sense. So h is 17 units. Theta is 58 degrees. And this one is 23 degrees. And the whole thing is divided by the sine of alpha, which is 23 degrees. Oh, the cosine rather of alpha. Yes, this is what we say. And now we just need to hand everything over to the calculator. They will tell you to how many decimal places are you supposed to round off your answer. So we'll be having 17 times the sine of 58 minus 23 divided by the cosine of 23. So correct to 2 decimal places, the length of AD will be 10.59 units. Yes, this is what we say. Now then, knowing what we know here, the next question is saying, please calculate the area of triangle ADC. Well, that's what they say. So, where is this triangle ADC? Well, it's this triangle that is not right angled. And we know that we can't use the half base by height in order to find the area of triangle ADC. No, we'll have to use the area rule. And the area rule, we know that it's similar to the cosine rule in that it needs us to have two sides as well as the angle between those two sides, which we call an included angle. That's what the area rule is saying. Very well. We now know the length of AC because it's given to us, right? And we also know the length of AD. We just calculated it. So this means we just need to know the size of angle A then, and we should be fine. And we know what is the size of angle A. We did find it in the previous question, but we found it in terms of theta. And we said angle A is 90 degrees minus theta. So you can just go on and say the area of triangle ACD is simply going to be half times AC, and you also multiply this by AD, and then you times this by the sine of angle A. You don't need to write a formula. You don't have to. There is no mark for the formula. But AC is H, and H is given to us as 17 units. AD, we just found it now. And theta, they told us that theta is 58 degrees, but angle A is 90 degrees minus 58, which has to be 32 degrees. And now we can press everything into our nice calculators. So when I press this into mine, I find that the area will be 47.70 units squared. Okay, so in the diagram below, PQ is a vertical tower. QR and S are points on the same horizontal plane, which means No, did I say P? I wanted to say Q, R, and S are points on the same horizontal plane. Yes, they're the ones in the triangle that's in the base. The angle of elevation from R to P is theta. Angle QRS is 120 degrees, the one that's in the base. And PQ equals RS, and both of them are x units each. Well, this is what they tell us. And when we carefully look at the case here, we can see that we actually have 4 triangles here. Well, we have many triangles actually, it's not even 4. There's triangle PRS, there's triangle PRQ, there's triangle PSQ, and there's also triangle QRS. So, oh, it's actually 4. Yes, I said it correctly, but that's fine. The most important thing is we have 2 right-angled triangles. That's triangle PQS as well as triangle PQR. Those are the 2 right-angled triangles. Everyone else is not a right-angled triangle. All right. Now then, the first question is saying, please determine QR in terms of theta and x. And when we look at QR, it is the adjacent side with respect to theta. And PQ is the opposite side. So this means we just need to find a trigonometric ratio that relates RQ to PQ. Is there someone who can tell us here what is that trigonometric ratio that relates RQ to PQ?
Tan theta.
Sorry, I'll see.
Tan.
Yes, tangent. Thank you so much for that. So that's what we should be using in order to find RQ. Well, we'll do that when we do 5.2. I think we should read 5.2 already, so that when we go to the whiteboard, well, we don't have to come back many times. Then the next question is saying, show that QS is equal to x times the square root of 1 over tan squared theta plus 1 over tan theta plus 1. It seems as if it's very much complicated, no? But that's fine. The first question we need to ask is, where is this QS anyway? And when we look at QS, we can see that, well, it's actually in the triangle that's in the base. It's not in a right-angled triangle, which means in order to find this QS, we can't use our normal trigonometric ratios. It's either we use the sine rule or the cosine rule. That's just it. But now we can't use the sine rule. Why? Because the sine rule does not have squares. We can only get a square from the cosine rule so that we can find the square root. Do you get that? Without a square, you can't get a square root. So it tells you clearly it can't be the sine rule. Cosine rule is the best way out. Now, we will have found QR in the previous question, and we are given RS. So we have 2 sides and an included angle, which is the 120 degrees. We have everything we need in order to use the cosine rule. So let's get on with it. But firstly, we need to find RQ, and as you told us, OC, we need to use tangent. So we say, well, according to the tangent of theta, RQ is the adjacent side. Oh no, tangent is opposite over adjacent. Okay? So the opposite side here is just going to be PQ, which has a size or a length of x. And we divide this by the adjacent side. The adjacent side is going to be RQ. Well, this is what we say. The RQ, we can see it's the denominator. And if you want to make the denominator to become the subject, you just take it and make it the subject. And you take what was already the subject and you make it the denominator. That's just how it works. And this is the length of RQ. We have now expressed RQ in terms of x and theta. So then let's go for the cosine rule. We now know RQ. We also know RS. Then it's really easy to find SQ. So I'm going to begin by respecting the cosine rule first and writing out the formula. You don't have to. But according to the cosine rule, the square of SQ is given by the square of SR, which is added to the square of RQ. Then we minus twice as much the product of those two sides. And we times this by the cosine of an included angle. In this case, the angle is SRQ, or you could have said QRS. Well, QR, you could have said QR, you could have said RS. The order is not really important. All right. So what? Well, easy. We just need to substitute. So now we have our SQ squared. And we can say, but what is SR squared? Well, it's just going to be x squared. Then we come back and say, but what is RQ squared? We just need to square that. So when you square the x in the numerator, you get x squared. When you square the tangent in the denominator, you get tan squared theta. Yes? And now you just need to subtract twice as much x, which is also multiplied by x over tan theta. Then you times this by the cosine of 120 degrees. Very well. So then, now you can come and say, well, what is it I see here? Well, nothing for the time being. So I can just write this as x squared plus x squared times 1 over tan squared theta. 120 degrees we know that it is a big angle. It's bigger than 90 degrees, so we need to use the reduction formulae. That's what we know. And x by x will simply get x squared. So I'll just write the x squared here. Yes. And well, we still have the 2 in front. And now we have 1 over tan theta. Now we say, well, what about the last one? The cosine of 120 degrees, we know that it's 180 degrees minus 60. And the cosine of 180 degrees minus, this is in the second quadrant, cosine is negative. So I can replace this with negative cosine 60 degrees. But you know that you're a learner, so you need to show all the workings. I'm just skipping the steps here. You had to show that you're using a reduction formula. Negative by negative, that gives us a positive, yes? So I still have my, well, now I can begin to take out a common factor actually, because x squared is there in every one. If I take it out, I'm left with 1 from the first one. If I take it out, I'm left with 1 over tan squared theta from the second one. This one becomes positive. If I take it out, I'm left with 2 times 1 over tan theta times a half, because the cosine of 60 degrees is 1/2. Yes? So now you have 2 multiplied by a half. And when you say 2 times half, you get 1. Yes, you get a 1. And now you can find the square root on both sides. So then the square root of x squared, well, I should have done that here. I don't like adding many unnecessary steps. So we could have found the square root right away at this point. Something in the chat box. Negative half. No, Aussie. It should be negative half, that's true. But I just decided to say negative times negative, and it gives me that positive. Yes. Now then, the square root of x squared, that's x. And the whole thing is left as it is. And since they wanted it in a specific order, then you can begin with the one that is squared, come back to the one that is not, and lastly, you can write the one here and say the thing. Yes. Well, this is what you could have said. And if you say this, well, they should be happy and award you all the marks.